is the simple 1D case for this kind of a 3D problem, where we are using spherical coordinates to really simplify the process. So here I have just used spherical coordinates to represent this Laplace problem, and we are integrating over this volume. So if we want to integrate just over r, the radius, we just want to integrate over this segment here, this line segment. So we just have to scale it with pi r square to take into effect the equation, the effect of the volume, right? And the actual integration will, in case of 3D, would happen in this kind of a domain, which is discretized into tetrahedrons, and we'll do this on Gmesh. And before doing that, we'll solve it on a simple 1D case, and then we'll go to the 2D kind of case, and so which will not be a sphere, of course, it will be an infinite cylinder, and then we'll go to the 3D case. And in this spherical case, of course, we have an analytical solution, and we are able to compare our solution with the analytical solution. And so of course we can do some error analysis. So let me show you how this mesh looks in Gmesh, right? So this is your 3D mesh, and this is discretized into tetrahedrons, right? And each tetrahedron will have shape functions or polynomials, which are basically 3D polynomials, and you could add more number of polynomials, and for doing this you increase the order. So this is done by adding more points onto each tetrahedron. You don't increase the number of tetrahedrons, but you just add more number of points. Okay, so you're just increasing the number of points, but not increasing the number of the tetrahedrons. Okay, so this is called as polynomial refinement, and if we increase the number of tetrahedrons, that is called as H refinement. Okay, so so this is H refinement, where you're increasing the number of you're really increasing the number of tetrahedrons, right? So both of them have different use cases. So if your solution is really smooth, you can just increase the order, and that would help. But if your solution is having sharp discontinuities, then the higher order elements would struggle to represent that, and they would oscillate. They would give you oscillations. So you can just use linear or lower order elements in case of discontinuous solutions. And this really applies to continuous Galerkin, which is the formulation that we are using. In case of discontinuous Galerkin, you can crank up the order despite having discontinuities in your solution. So now let's return back to our simple 1D case, and as you can see, we have just reduced it to a simple isotropic case in which there are no constants left, right? You just have this simple term, right? And now let's try to understand how this boundary Robin term comes about. So I'll just derive it quickly on a whiteboard. So let's just do that. So let's consider our test case, where you have, this is your origin, right? And this is your sphere boundary, r is equal to 1, and this is your outer domain domain truncation, the radius at which your domain is truncated. So we want to really represent an infinite domain, but we are just basically truncating the domain, right? So we want to capture the effect of this the solution at infinity. Okay, so let's just do that very quickly. So let us consider what you could call as an infinite element. Right? So this, so let us consider this this point of the element is at r, which is the point at which we are truncating the domain, and at this point is at infinity. Okay, and here you have phi of r, so this is unknown, right? And here you have phi of 0, phi of infinity. So this is typically your known, because this is like a far field value which you know, and in this particular isotropic problem you have a very easy analytical solution, and that solution is just phi is equal to a constant upon the radius, right? So at infinity, you just have r is tending to infinity, right? So your phi just tends to 0, right? So you have a far field value for phi, and this phi of infinity is just tending to 0 as r is tending to infinity, right? So you already have this boundary, and now we want to incorporate this effect into our actual in our actual boundary at which we have truncated the domain. So let's just do this. So let's map this to a master element first. So our master element will run from 0 to 1, and we have these two test functions. Psi1 is equal to 1 minus psi, which is this decreasing function, and you have psi2 is equal to psi. So this is your increasing function, right? And so basically you have r of psi, you have this mapping r of psi is equal to r, which is the truncation, the radius at which you are truncating your boundary, upon 1 minus psi, right? So as psi tends to 0, you recover r, at as psi tends to 1, you are recovering infinity. So so since we are dealing with derivatives, so now we want to so let's just derive dr by d psi, because we need it in the isoparametric mapping. So this is simply r upon 1 minus psi square, 1 minus psi square, right? And this is the same as r square upon 1 minus psi square upon 1 upon r. So remember that r is equal to this term, so we could just simplify this as r square upon r. Okay, so now let us try to understand our derivative. So we want to represent d phi by dr, right? So let's just expand this as a series of polynomials, right, inside the element. So we would just do phi r into d psi 1 by dr plus phi infinity into d psi 2 upon dr. Okay, so this is just like so we are just using our piecewise continuous approximation. So since we have the master element and physical element mapping, so let's just use that. I'm really sorry for my handwriting. I hope you can understand it. Right, so this is our mapping, and so this is phi r, which is your unknown. This is just this is r upon r square, right? So yeah, that's right. So this is r upon r square, right? Because this is the node which is situated at the boundary, the truncated boundary, right? And this is just minus 1 because we are using linear elements, the derivative of the linear Lagrange element. Let's write this as phi infinity, and this is your r upon r infinity square, and this is plus 1. Okay, so as r tends to infinity, this term as well as this term is basically going to 0. So as r tends to infinity, you just have d phi by dr is d phi by it is d phi by dr is equal to minus phi r upon r. Okay, and in this case we have just used r equal to 12. Okay, so this is basically the same case which I've shown here, right? So this is how the boundary term has been derived. So this is the Robin boundary condition, and now let's try to understand how we are going to apply this to our finite element formulation. So again, so this is our equation, right? So let's multiply it by a test function psi, and let's integrate it over r. Then let's apply integration by parts. So we'll have two terms here. So one will be the green term, which is applied on this 1D structure, and then you have the boundary term, which is this term, right? And so you have this d phi by dr here in the boundary, and this is our boundary condition. So we know d phi by dr is equal to minus phi by 12, right? So we'll just plug this into this part, this guy here, and remember this phi is only the phi at r, which is the phi at the boundary. So in this simple case, this is just a point integral. Okay, so let me return back to the whiteboard. So in this simple case, this is your r, and let us consider this as the final element near the truncated boundary. Okay, and so you will have this as, let us say, phi r. Okay, and if I just call this as phi r minus 1. Okay, so really I am dealing with the boundary point which is situated only here. So this is just a point integral in this case. So you are having this psi into r square into your d phi by dr, right, dotted with the unit normal. So this was the term which was coming out of our finite element formulation, right? This guy here, right? This blue term. So so this n is just the unit normal in the outward direction, right? So here this is just a point integral, but if this was a 2D case, okay, and let's say if I was using a triangle to represent this 2D case, okay, so this would rather be a representation like this, okay, then I would have two nodes here, and I would have this boundary, and in that case the boundary term would be something like test function into flux dotted with the unit normal in the outward direction. Okay, so this would be integration over this boundary gamma. Okay, so this is omega, which is your domain inside, and gamma is your boundary. So really your boundary integral is this term at the boundary is basically a boundary integral. Okay, so in this case, in this 1D case, you just have a point integral. In a 2D case, you have a 1D integral, and in a 3D case, you would integrate a 2D face, and you would just get this term. Okay, and this term is really on the right hand side. So you have your stiffness matrix K multiplied by your unknowns vector U, or in this case this is phi, right, and this is equal to your force vector F. And so this boundary term really exists, this flux term really exists in your force vector. Okay, and so since you have an unknown here, so you have to really bring this unknown into the stiffness matrix. So to do this, here this is in this 1D case it is very simple. So in your stiffness matrix, you have this final row of your stiffness matrix is multiplied by your test function psi r, right, and here you have psi r at the end. Okay, and our boundary term is basically psi r into your r square into your d phi by dr multiplied by the unit normal. Okay, so it's very easy to do this. So d phi by dr is basically we have already derived it. D phi by dr is equal to minus phi by r, right? So this term is just r square upon minus phi r upon r, right? So this is just psi r into phi of r, okay, minus. So really what you have to do is, so this term, since it exists here, right, so you could write it as 0 plus this guy. So let me write it as r, or let me write it as RO, that is the Robin contribution. Okay, and I just have to take this Robin contribution and add it to the last column of this matrix. Why the last column? Because it is representing the trial function associated with this node. Okay, so this is the test function psi r, and there is also another function on this inside this element, but it is identically 0 here. So I am just adding this boundary integral onto this final node. Okay, so really you just have to take RO and add it to this point. Okay, so it's very simple to do this Robin term assembly, and we'll now actually do this in the coding. So let's do this now, and we'll do this in the next lecture, where I'll live assemble all of this, the 1D solver in front of you in MATLAB, and I'll also provide a working code in Python and Julia. So this is going to be very simple, and let's also try to do P refinement, H refinement. Let's look at how the error converges, and once we do that, we are ready for going towards 2D and 3D problems. So I thank you for your attention, and now let's meet again in the next talk, where let's start off with some actual coding.